Hey everyone, this is Travis Clip, and today I'll be presenting the two-sample normal model in Bayesian modeling. First, I'll go over some of the theory using the reference prior, and then with independent proper priors, and then I will analyze a real data set using R. And the viewer should be advised that they should already have some familiarity with Bayesian modeling and the one-sample normal model. Okay, so starting off with the two-sample normal model with the reference prior. To set up this problem, let's first consider two independent samples of data, which are normally distributed. Okay, so we have the first sample with n1 observations and the second sample with n2 observations, and then the associated mu and sigma hyperparameters. In Bayesian statistics, we're actually going to use the precision, which is 1 over sigma squared, and we have that for each sample. So there's two of them. And the likelihood of a two sample is the following. It's this following equation right here. So with tau and the exponential. And we define the standard and proper reference prior as follows. So 1 over tau 1 times 1 over tau 2. And we could derive the posterior distribution in the following way. Okay, so we simply multiply the likelihood times the prior, and it's the exact same as a one sample normal, except there's two of them. And the prior, it's this -1 right here, because it's just 1 over tau, and times the previous equation. From this information, we could also derive the marginals, and the marginals for each sample, since there are two samples, it follows a gamma for the marginal of tau. We have the gamma distribution, which has the following parameters: n minus 1, where n is the number of observations, n minus 1 over 2, then n minus 1 times sample variance over 2. Then the marginal for mu follows the t distribution with n minus 1 degrees of freedom, with y bar and sample standard deviation over square root of n. Then the conditional of mu given tau in the data follows a normal distribution with y bar and 1 over n tau. The sample from the posterior, we could use the sequential method. We first sample from the marginal of tau that follows the gamma distribution I just discussed, and then the second step would be to sample from the conditional mu given tau in the data, which is the normal distribution I just discussed. Okay, and we also want to discuss the independent proper priors model. Okay, so let's consider mu to be normally distributed with the parameters a and 1 over b, and that's independent from tau, which follows the gamma distribution of c and d. And keep in mind again that we denote the two samples by I for I equals 1, 2. Then we could try to derive the posterior by multiplying the likelihoods times the priors as follows. It's this big equation right here. And yeah, so to sample from the posterior, we need to use a Gibbs sampler. And to do that, we need to actually derive the conditionals. Okay, and the conditionals are exactly the same as the one sample, except there's two of them. And conditional for tau given mu and the data is the gamma distribution with the following parameters. Okay, and then the conditional of mu given tau, it follows this normal distribution. All right, so with this information, we could set up the Gibbs sampler. The Gibbs sampler operates the same. We start off with the starting point, or the initial guess, and then we generate this Markov chains for the two samples, okay, and for a number of iterations. And if m is a state of the chain, okay, so if we have mu and tau at some arbitrary state of the chain, to attain the next step, you do that as follows. So you first generate tau m plus 1 from the gamma distribution I just discussed. Then you generate the mu by plugging in the previous tau into that normal distribution I just discussed. And you do that for a number of iterations, so you have this Markov chain for both samples. Okay, and we also want to find the hyperparameters for the normal distribution, and to do that, we have to ask an expert the following. So for A and B, and for each sample, we want to have them answer what's the best guess for mu. And given that information, what's the largest reasonable guess for that mu? So value that only has a 5% chance that mu would exceed it. So like the 95th percentile of mu. And then we set the best guess as the mean, A. And for number C, we plug into this equation. So C equals A plus 1.645, which is the 95th percentile value, and then times 1 over square root of B. So from the question 1, we get the number A, and from question 2, we get C, and we want to solve for B. So that's how we get the equation. So we get the hyperparameters for the normal distribution. And for the gamma distribution, it follows kind of a similar process. We start with, so for the gamma, C, and D parameters, we have to ask an expert about the percentile of the data and then work directly with the prior distribution of sigma squared. So the percentile of some alpha level equals mu plus Z alpha times sigma. And the questions we want to ask are, what's the best guess for the percentile? And then given that information, what's the largest reasonable value for that percentile? So the percentile of that percentile. So with this information, we plug in. We want to solve this 2x2 system of equations for each sample to get the parameters. So we set the best guess we obtained earlier for mu, that set that equal to A, and we have sigma equals the percentile minus A over Z alpha. And then if we let P be the 95th percentile of that percentile, we have the inequality as follows. So sigma less than P minus A over Z alpha. And you have to remember, if tau follows the gamma, sigma squared therefore equals the inverse gamma with C and D, and the mode is D over C plus 1. Okay, and now to set up these 2x2 systems of equations, we have to set the prior mode of sigma squared to the prior guess of sigma squared. So then D over C plus 1 for each sample equals the percentile minus A over Z alpha squared. Okay, so that's the first equation, and the second equation is given in number 4. So at the 95th percentile, we have the following inequality. So that we have tau is less than Z alpha over P minus AI squared. So we want to solve these 2x2 systems of equations, and then you can do that numerically using a computer program. And so we just simply plug in this information. Okay, and now I'll present a real dataset example where I implement some of these algorithms.